organizing this talk. I am Yixu Wang from University of Maryland at College Park. Today, I will present the work Approximate Holographic Error Correction Code with power law correlations. The work is done with Chunjun Cao, which is our postdoc at Maryland, and Jason Pollock, who is a postdoc at the University of Texas. So let's start by the outline. So I will talk about the motivations, some constraints on the construction of holographic tensor networks, and then I will present a concrete construction of a hyperinvariant mirror model. I will explain what does it mean by hyperinvariant mirror along the way. So the motivation is we are moved by our great predecessors. Multiple tensor network models have been proposed as discretized models for the ADS-CFT duality. They capture some nice features of the duality, yet fail to manifest others. So the first one is the multi-scale entanglement renormalization ansatz, which is abbreviated mirror. And let me show you an illustration like this. So if you are not familiar with tensor network, let me give you a crash course. So a tensor network is a pictorial way of showing tensor contractions. For example, if you have some T mu nu, you can draw something like this. So the legs represents the what they call bound dimension, or actually the number of the indices of the tensor. And if you do tensor contraction, for example, T mu nu, G mu nu, then you draw another tensor for G and connect their legs together. Of course, here you have double contraction, so you connect their two legs together. So this is the idea. So for mirror, the construction looks like this. It has some isometries, which does the work of chorus graining because it sends two legs to one leg. In that sense, if you pass through this tensor by doing tensor contraction, the degrees of freedom is eliminated by half. So in this sense, you are doing chorus graining. So another concept that will be usually referred to is the so-called super operator. So as we said, each tensor can be written like this, and if we insert an operator here, and we are able to do some contraction, so by doing contraction, we actually append a tensor network upside down like this. And in terms of formula, we write, let's say this is O, and this whole thing is W. In terms of the formula, we write W dagger O W. And this sends the operator O to another operator, which we call O prime, who has support on this leg, something like this. In this sense, it pushes an operator from a lower layer to a higher layer, where the degrees of freedom is reduced. So we call this chorus graining processes, and we call this operation a super operator, or ascending or descending super operator, by depending on which direction we look. So this is mirror. It has the advantage that it's somewhat
Sorry.
captures.
Did you say pushing an operator up is the same as a super operator? I didn't get this point.
I mean, the effect of the super operator is to push an operator up.
Okay. So as in, if I sandwich, so is this green thing basically W that you have just written?
Yeah, this green thing is W.
Okay. Then if I sandwich O by W dagger W, then essentially the operator is moved up one layer.
Right.
Okay.
Yeah, this is just usual error stuff. You know better than me. And we say mirror, it is a successful tensor network model to capture some feature of ADSFT in the sense that it can roughly capture the RT formula for entanglement entropy, by which I mean if you can sort of like asking what's the entanglement entropy here, you sort of cut the legs into the bulk, and it is roughly the RT formula, something like that. However, it has its own drawbacks that we know it is not compatible with the hyperbolic symmetry, even the discretized hyperbolic symmetry. So we may not expect to put it properly on ADS background.
Oh, sorry. Why do you say even discretized hyperbolic symmetry is not possible?
For example, let's say you have multiple tessellation of the hyperbolic, and you can hardly find a tessellation that looks like this. So this is basically the ideal.
Okay, okay, so as in you if I want to separate things into disentanglers and isometries in this alternate layered form, then it is not possible. Then it is very difficult to find any. Well, it is not possible to find any tessellations. That. Okay, okay, sure.
Do you have some other construction in mind that can fit this tessellation? Or maybe you can tell me.
What I have in mind is that what if I just ask if there's some appropriate tensors that are repeated in all that are in every. So I don't demand that there is this separation into layers. Rather, like what you're going to talk about, this perfect tensors code. Every tensor take every vertex in the network, you pick the same tensors, so you do not separate it into a layer of disentanglers and a layer of isometries. Then you would preserve more symmetries.
So basically, we will talk it later, saying that if you put everything as if you put every tile the same isometry, then that won't work either, in the sense that it will not give you a non-trivial correlation function. But yeah, and if you say, okay, I put some weird stuff, if we put some weird tensor which does the work of isometry and disentangler both at one tile, what will happen? I actually didn't try, so let me say I don't know.
Okay. Please go on. Sorry, just curious.
Yeah, sure. And then someone say, okay, we don't have the discretized hyperbolic symmetry for mirrors, then what can happen if we put our tensor network directly on hyperbolic tessellations? And some proposal was given in this paper talking about hyper-invariant tensor network, and the construction is like this. You really deal with a tessellation. This is 7-3. So by 7, I mean it is tiled by 7 side polygons, and by 3, I mean each vertex it is attached to 3 this type of polygon. So you have 2 types of tensors. You have A at the edge and B at the A at the vertex and B at the edge, and you don't require them individually to be an isometry, but you require some grouping properties like this. You require this combination to be an isometry. So does this. And let me introduce some definition in our paper too. So we call any tensor network put on this hyperbolic tessellation and edge mirror. And if each of the tensor is an isometry so that it can be contracted on its own, we call it locally contractible. However, this type of condition that you require the grouping of the tensor network to be an isometry, we call it quasi-locally contractible. This is some definition that will be used later. And this hyperinvariant tensor network, of course, has a nice property of the hyperbolic geometry. However, we are not quite sure how to interpret this as a quantum error correction call. I think we are able to, but it was not done in that paper. Then we may ask, okay, why do you want this to be a manifest quantum error correction call? This is for the sake of doing bulk reconstruction of ADS-CFT. So by bulk reconstruction, we mean a concrete way interpolating between boundary and bulk. And if you are an error correction, you can manifest some properties of so-called HKLL formula that you can have you can have some freedom in choosing your subregion, which is guaranteed by quantum error correction property.
Sorry, actually,
yeah.
Is there any reason why they call this non-locally contractible? Because the tensors still look pretty local.
Yeah, I mean, we call this quasi-locally because it is not strictly local. It's like some block here, and you can argue whether these blocks themselves can. I mean, you can argue whether these block yourself.
You mean they start repeating themselves after several steps? Therefore, I would block them together. Is that the point?
My point was, it is not strictly local to its every edge, but it is local in the sense that, okay, you have some grouping here and grouping there.
So what do you mean by not strictly local to its edge? It looks very. I don't understand what you mean by local and non-local here.
By local, I just mean you respect your. I mean, every point is an isometry, something like that. It is not like you necessarily have some long range effect in the sense we call non-local. We just talk about the most trivial definition of local, just like if this is an isometry itself.
So if you mean that if I have to keep okay, you meant that if it is not an isometry, you have to look for the minimal collection of stuff so that it is an isometry.
You need to group different things together and require them to be an isometry, not each A and B is an isometry.
I see. Okay, this is what it means by isometry. Good. Okay, now I understand.
This is like 4:2 isometry. This is 5:2 isometry.
Okay, so you say individual tensors here are not isometries, but if I take this combination, then it is an isometry. And you would call that one local unit.
Yeah, one quasi-local unit, something like that. You may argue, okay, if I really like break them down into these blocks, and we zoom out to view these blocks as to view this block as a point. Can it be some other non-regular tessellation of hyperbolic plane? Yeah, maybe it can, but we
Okay, okay.
didn't
I
investigate.
understand what you mean by locally contracted. Because the point is, if they are isometries or unitaries, then when you contract two-way functions, a lot of these things cancel,
Right.
and therefore you call them locally contractible. Okay,
Contractible.
now I
Yeah,
see. Yeah, I was very puzzled when I look at your paper.
sorry.
Fine. Thanks.
Yeah, so we didn't emphasize that these AB are just some tensors which obey some high permutation symmetry, but they are not themselves isometries. Only by grouping them together can you get isometry. Yeah, this is hyper-invariant tensor network. And then the next is the heavy code, and we base ourselves heavily on this as well. So it is based on the 5-4 tessellation. And at each tile you have a 513 stabilizer code. And if someone are not familiar with quantum error correction code, 5 means you have 5 physical qubits, i.e. 5 legs here. 1 means you have 1 logical qubit, which is a bulk qubit represented as the red dot here. And 3 means the code distance means you at least need weight 3 operator to flip the information of the logic qubit. So this heavy code has nice features. It is based on hyperbolic tessellation, which is good. It is manifestly a quantum error correction code, which is also good. However, it has the drawbacks that for 2 generic points, the 2-point correlation function is the connected part of 2-point function is 0. Actually, you can have 2 points whose connected 2-point function is not 0. However, these types of points will take an exponentially small portion of the total points if you allow your tensor network to have larger and larger layers. So we can say a typical 2-point function in this tensor network is 0, which is of course not the behavior of the CFT, and this is the main goal to fix in our paper. Last but not least, let me mention the random tensor network. The idea is like you sort of randomize your state here, and by randomizing, you can use some Shor lemma stuff to have a nice property in terms of calculation. However, it is very hard to do the decoding work as a quantum error correction. So error 1 has its nice features, yet some drawbacks, and we try to merge different nice features, as many as possible. We can indeed do this, but we need to make things slightly more complicated. And I'll tell you why this is the constraints. So before moving on, let's review some terms. So some of them we have mentioned before. A hyperinvariant mirror, or H mirror, is just a tensor network built on the dual graph of the uniform hyperbolic tessellation. For example, this hypercode is an example of H mirror. So is this hyperinvariant tensor network. Then an H mirror is regular if it is built from a regular hyperbolic tessellation. By regular, I basically mean the tessellation is done by only one type of the polygon. If the tensors over different tiles in this network are all identical and permutation invariant, then we say it is completely regular. So the example is the happy code. Everything is the same, and you can look it up and to see that this 513 stabilizer code encoding isometry is indeed permutation invariant. So this is an example of the completely regular. However, this hyper-invariant tensor network has two types of tensors, so we don't call it completely completely regular. The next definition is locally contractible, which we have explained in detail in that hyper-invariant tensor network example. If each tensor is an isometry, we call it locally contractible. If they group together to become an isometry, we call it quasi-locally contractible. Then we introduce our definition of isometry. If a tensor of degree n, by degree I mean n legs connecting to the node. So if a tensor of degree n contracting n minus l legs of the tensor with its conjugate transpose yields identity to L copies of identity, then we call it L isometry. And we can define the permutation invariant of the isometry as well. So if you contract any of the, let's say if you contract any of the lines here, let's say here this is a degree 4, and suppose it is a 2 isometry. If it is permutation invariant, if you contract this with this, or this with this, or this with this, they all yield identity to the power of L, then this is what we call permutation invariant. So let me remind you, maybe you don't need, this is a pictorial way of representing isometries. You contract the two together and you get a bunch of straight lines, which are the representations of identity operator. And we now present a so-called no-go theorem. So we have a lemma, which says a completely regular edge mirror is locally contractible only if it has tensors that are at least 2 isometries. And the theorem says a locally contractible and completely regular edge mirror always contains a trivial connected boundary 2-point function. So before going into the details of the proof, let's first build up some intuitions. So why we are interested in locally contractible and completely regular? It seems a very strong constraint. So basically, you can say, okay, locally contractible actually represents it is not microcausality, but let's say it represents the causality condition of our spacetime. So we don't want our spacetime to be sort of non-local. And the completely regular condition respects the isotropic and homogeneous property of the ADS space, at least empty ADS space, and so we want our tensors to be the same. So this is the idea of why we consider this type of edge mirror. However, it cannot help, basically because we require them to be 2 isometry, and there are too many maximally mixed properties there, and it will push the operator to be a trivial operator, or by trivial I mean identity, and this will not contribute to the boundary 2-point function.
Oh, sorry. I missed it again. What is two isometry again?
Oh, two isometry is like if you have a fuzzy ball, let's call this a tensor, a node in tensor network. And if you contract all but two legs, it is an isometry. This is two isometry. Say if you have 6 legs here, if you contract any 4 of them, they are isometry like this.
Okay. What if I contract 3 or any 4 of them, not just
Yeah.
I can take any 4. So it is fairly close to a perfect tensor because I can pick out any 4, but it's weaker than a perfect tensor because in perfect tensor I can pick any group of legs with any number and it is still an isometry.
Yeah. It's weaker for actually yeah. So let's say it has a property like if you are an L isometry, then it is necessary an L prime isometry if L prime is smaller than L. For example, if you are a two isometry, you can contract one more leg and it is still an isometry because the remaining
That's
one
true.
is
Yes, I
yeah.
understand. Yeah.
So basically perfect tensor you can call it 5-degree 4 isometry, then it immediately guarantees that any
Oh,
lower is
I see. I see.
3 isometry, 2 isometry, 1 isometry, something like that. Yeah.
I see.
This
I see.
is this is the trick in the definition.
Okay.
Yeah, so let's then jump into the proof. So the proof of lemma is sort
Sorry,
of like
when you said something about your intuition, I missed the point where you said something becomes identity. Can you just say that once more? You said you push the operator and then something becomes identity. Can you say that just once more?
yeah. So I will show it
Oh,
here, but
okay.
I'll just give you a preview. It's like you do the super operator on any operator O, and it gives you some constant times identity operator.
Uh-huh.
Oh yeah, then
Oh,
identity
that O
operator
is
does not
identity.
contribute. No, O is not identity. This is any operator, but you will realize that the information of O is contained in this constant in the front, and the
Okay. But
operator itself.
O is something like it is local. It has only one leg.
Yeah, it has only one
Oh,
leg
okay. Then I'm
support.
happy because
Yeah.
okay.
Sorry.
Good.
Yeah, so maybe the proof, or you can sketch the proof. Then let's again sketch the proof. Let's do the sketch and do the proof. So why do you need two isometries arrow? This is because you want to do local contraction. So let's focus, let's say, this type of the tensor. Yeah, okay, I forgot something. So the starting point is, what do we mean by layer? So we need to artificially choose a center. It is depicted as a pentagon here. And once we choose a center, we can define the layers by growing our tessellation out. So you can append another polygon adjacent to it, and we call it layer 0s, and this is layer 1. If you need to grow twice to get this one, this is layer 2, etc. And in this way, you can sort of uniquely assign each tile to a number which is its layer. And so if you define the layer, you can define the inward and outward direction. By inward, I mean a higher number of layer connecting to a lower one and vice versa. Okay, so let's focus on this one. So it is because we want to do local contraction. So if there's nothing happens here, we wish it to contract directly to some legs like the appending legs like this, right? Let's say we want this if we contract something like this. We want it to be something like this so that we can do contraction of the next layer and it will not involve information from other places. However, if you are one isometry, this means you can only say this thing is an isometry. You need sort of know the information on this leg, whether there is an operator insertion here will matter. And this needs some information from other points. And in this sense, if you need information from the inward direction, it is no longer a locally contractible tensor network. And you can see from the geometric point, these types of the points always exist in the regular tessellation of the hyperbolic plane. So this is why in hyperbolic, if you require completely regular, let me remind you, this requires every tile has the same tensor network. So since you have such type of the tile, you require every tile at least to be 2 isometry. So this is the
for it to be for it to be locally contractible.
Yeah, right.
So basically, something like I need to see that when I do contractions, I have enough legs contracted to get some identities. That would be called.
Yeah. That's correct, and you can see it from the flow of the information. Let's say, because like you only want the information from its downstream to do the contraction. You don't want the information from its upstream to get in, and so that's why you can always find point who has like 2 upper streams. So this is why you need 2 isometry.
I see. I understand. I see. Topologically, it has to have at least 2 legs going up. But
like right.
Is that does that depend on the fact that you are working on with sort of 2 dimensions?
2 dimensions.
What if I do a 3-dimensional network? Do I still need just 2?
Let's see. We didn't think of it before, but so this 2 is used to construct loops. You need this type of edge to form a loop. Otherwise, it becomes a tree. Yeah. So basically, if you still have a tree in higher dimensions, then it's still 1. But
right, if I want
if
some
you have
network
some simplex. Yeah, I may suspect it scales as dimension because maybe you can say, okay, I need some closed surface for the simplex, right? And it depends on like how many edges, right? For example, you have like this tetrad, and you really need 3 legs connecting it to become a tetrad, I guess.
Okay, but yeah, that sounds like an interesting thing to think about. Thanks.
Yeah, this is my guess that these 2 things depend on dimension, as you point out, and maybe in higher dimension it requires the isometry, something like that. Okay, this is the proof of the lemma, and then the proof of the theorem. It is more or less manifest, so we need two isometry. However, when we look at this node or this tile, it is a two isometry as well. And let's say what will happen if we insert an operator O at this leg. So we can do contraction, which is something like this. O. So we required permutation symmetry. So by contracting these three legs, it becomes something like this. You have an O here, sorry. O. Then something like this. This is nothing but trace O times rho I, where rho I is this maximally mixed state. And this is an identity operator. So we can say if we call this isometry W again, we say W dagger O, W equals to trace O rho I times identity operator. This is what we mean by saying the super operator of the two isometry always pushes a weight one operator to identity.
Okay.
And this is incompatible with the error correction property of the code in the sense that it will always correct weight one errors if you view the insertion as an error, something like that. Yeah, so if we insert at this type of circle tile, we see it immediately gets something trivial. If we insert something at this type of square tile, we will see in the first pushing, it will go generically, it will go to some weight two operators supported here. However, you will see that again, when you push a second time, it will encounter something again like this, and they will become trivial within two pushes. So maybe you can find something like, for example, here after one push, its direct ancestor is a circle and a square, and you will realize a circle becomes trivial while a square is non-trivial. However, if you would like to get a non-trivial correlation function in a long scale, you would like to find some point whose ancestors are always a square plus a circle, then at this, and then a square plus a circle, and these types of the points is exponentially rare if you go deep into the boundary. And this is why for happy code, we say the non-trivial two-point functions are exponentially rare. Yeah, so we have sketched the proof, and we excitingly get some not so exciting results. And so that's why we want to circumvent the theorem. The most elegant setup does not work, which is a pity, but we need to live on. And we can relax some conditions to make it work. So the first attempt is to relax the completely regular network to a regular one. Recall, a completely regular network requires an identical tensor networks on each tile, which is strong, and it requires permutational invariant. So we can relax either of the two conditions by allowing more than one type of the tensor networks, which is what we did in our paper, and by reducing the symmetries of the tensors. by not requiring permutation invariant of the tensor network. In this sense, you can only contract the tensor in a particular way, not any way you like. The next attempt is even relax this regular condition by saying build the network beyond the regular tessellation. For example, you can construct the tessellation using two types of the polygons, and some work has been done along this line. And the third attempt is to relax the locally contractible condition to quasi-locally contractible, which is already a concrete example. A concrete example can already be seen in the type of invariant tensor network example. And from now on, we will focus on our construction that is allowing more than one type of the tensor. So the construction is like this. We have spotted that actually, apart from the top tensor, which is chosen arbitrarily, we have two types of the tensors. So we have two types of the tiles, which have slightly different environments after we have chosen the top tensor. This is the so-called vertex polygon and edge polygon. By vertex polygon, we mean this kind of square tiles which have two edges connected to its upper layer, like this. And by edge polygon, we mean this type of circle which only has one leg connecting to its upper layer. The construction is for vertex polygon. We put a direct product of two copies of the stabilizer perfect code, which is what happy code is. We don't change much for this vertex polygon. And for edge polygon, we use a tilde version for the two copies. And in the paper, we also showed this is a 502 code for 4 qubits. And for top polygon, we adopt a similar tilding techniques, since top polygon does not contribute to the long-range behavior a lot. Let's just don't discuss it. And then we present the tilde construction for edge polygon. So here, each leg here represents a qubit or a 4-dimensional Hilbert space, while each leg here is a qubit. So each one is an encoding isometry for the stabilizer code, and we take direct product of them, and we introduce some parameter, cosine theta and sine theta ij. In the first line, it is just the perfect code, and in the second line, we pollute our perfect code with some z arrows. Of course, you can choose other xy, but we just choose z as an example. So how do we add arrows? It is something like we pick out all different arrangement of the legs and add z. For example, there can be z inserted at leg 1, 2, or 1, 3, 1, 4, 1, 5, 2, 3, so on and so forth. In total, it has 20 terms. Why we choose this construction? For the one thing, we want it to be as close to a well-established quantum error correction code as possible, so that it can have some nice error correction property, at least approximately. And for the other, you can see, actually there's only one consideration. That's what I have said before. You can see that for sigma small, it is more and more close to the perfect tensor before, and once sigma, I was constantly saying sigma, it is actually theta. When theta is 0, it reduces to the perfect tensor code, and the whole thing reduces to a double copy of the happy code, and the double copy does not commute, so this is simply happy code. And if we turn on this theta, the two copies has some communications, and it is actually an approximate quantum error correction call. By approximate, we mean we tilt the embedding isometries a little bit, and we can have some overlap between one state and zero state. In this sense, we can only recover the logic qubit information approximately. So we have the isometry condition, that is, we require the parameters to satisfy this equation so that this whole thing is an one isometry. And to retain the maximal symmetry, we usually choose this theta ij to be all identical for different I and j, and this is actually a one parameter tensor. And as promised, it will produce the power law decay. Why? This is because let's recall the proof. If everything were two isometry, then this pushing will give you trivial output immediately. However, this type of tilted tensor is a one isometry. So this guarantees that this will not give you a trivial result. Rather, it will give you some different operator O prime, which depends on the content of O for weight one operator insertion. So in this sense, by introducing a tilted code, we kill some redundant and maximally mixed property, and this helps us to produce the power law result. So this is how power law is generally produced in tensor network. Maybe you're all familiar. We just go through it quickly.
But can I just ask a quick question?
Yeah, sure.
Why? What inspired you guys to think of taking this double copy?
Oh, double copy is to sort of like get the isometry between copies, because if you do the simple thing of this plus z plus z plus this thing, something like that, this is the simplest thing you can think of, then this is not an isometry in any sense. So then,
Okay, so you want to make it still some you want to keep it as a one isometry, is that the point?
yeah, we want to keep it a one isometry, and we want to make it as symmetric as possible.
I see.
So this is why we choose this double copy, and we can insert the arrows in a symmetric way. Yeah.
But can I just directly look for tensors that are one isometry with 5 legs? Or are you saying so? This tensor it has 5 legs, and so it would be in a space of 2 to the 10 dimensions. Is it that does there exist one isometry with only 5 in 2 to the 10 dimensions rather than here 2 to the 20?
Oh, 4 to the 20. Yeah. I think yes, sure, of course, but the idea is we want this isometry to be close to some to some error correction code as well. So this is the starting point why we add arrows to error correction code to generate this type of isometry. Then if you totally say, let's don't worry about error correction code, we just want anything simple, then sure, you can find one isometry in 2 to the 10 for sure. Oh, by the way, 2 to 23 something. Yeah, sure.
I see. Okay.
Yeah, this is for the sake to be close to some non-quantum error correction code that we did this type of construction.
I see. Thank you.
Yeah, and we were saying this power law decay is the usual behavior for this type of the coarse-graining model. So you have operator here, you have operator here. Let's assume they are the eigenoperator of your W dagger W. So they will become, so W becomes some lambda O, and you are push like this, and they will meet together somehow. And for each layer you have pushed, you pick up a prefactor, a coefficient like this, and you cross L layers. And here L is a log of I minus J, where I, J are the indices at the boundary, and roughly this is R in the discretized sense. And log L is log R, and you can rewrite this in terms of something like this. And this is basically R to some power, and this is why we call it power law. And this delta alpha beta are just a log of this dominant eigenvalue of the super operator, and they are the effect conformal dimension of the boundary operators. This is the usual story of how power law is generated in tensor network. And this lambda is the average of the dominant eigenvalue of the super operators. So basically, the idea is that if you are familiar with mirrors, there's the average over the left, mid, and arrow super operator. Here it is the same idea. So for a given operator insertion, you go through a fixed set of the super operators. However, it is actually more complicated if you deal with this hyperbolic toweling, because super operators have different types and they are highly dependent on your initial starting point. So let's talk about a typical insertion point, and we can talk about a typical coarse graining processes. This is the same idea as averaging. It is, then we can talk about the probability of different types of the super operators showing up. Here is a summary. You can have weight 1 operator going through this imperfect tensor to a weight 1, or weight 1 going through this perfect tensor to weight 2, or something like this, weight 2 to weight 1, weight 2 to weight 2 through this combination. And 2 to 3, 3 to 3, and 3 to 2, something like this. And you can really calculate what's the probability of each type showing up in a typical coarse graining process, as we discussed before, something like this. In this sense, in this sense, the P here, we know we can actually calculate. This is just a geometric consideration, and this lambda thing really depend on your parameter theta here, and actually you can have a parameter for your stabilizer perfect code as well, which is the bulk state here, which will set your stabilizer isometry. So you have so the lambdas depend on the parameters of your tensor, while P depend solely on the geometric consideration. And we only proved that this type of power law decaying property exists. We didn't calculate to high precision what will it be like. We only show it can be done. And there is a bonus that this type of the tensor network will give you non-flat entanglement spectrum of subregions, as opposed to happy code, which is known to give you a flat entanglement spectrum. If you're not familiar with entanglement spectrum, this is a way of saying you collect the nth Renyi entropy trace. Maybe there is a log trace row minus log trace row n. If it is flat, then to any order n, it gives you the same result. However, this is an undesirable feature of the tensor network because we know in real safety it does not behave like that. And by doing the toweling, we are able to calculate some small subregions explicitly and show that this type of tensor network indeed produce a non-flat Schmidt coefficient, thus it will produce a non-flat entanglement spectrum.
If it is too non-flat, then RT formula would break down.
So you can tune your cosine theta here to be small and to make it not so flat. To make it not so
right.
So steep, something like that. Yeah.
Yes, then maybe there would be a way to identify this permutation from this perturbation from exact being an exact perfect tensor.
Right.
G Newton is controlling some scale.
That's what we have in mind as well. We think of this toweling as some G Newton effect, indeed, and this is what we advertised afterwards. So let's do the summary.
Okay, so, but do you have an expression? Let's say how the G Newton should scale with this sine theta.
No, we don't have, and this is because like it depends on the logical state here as well. So this is a little bit more complicated than saying we can write down a one-to-one correspondence. But indeed, this gives us some new arena of doing things. Let's do the summary. And we examine some general properties to construct a holographic quantum error correction code, which also supports power law 2-point correlations. We obtained a no-go theorem along the way, saying that locally contractible and completely regular H-mirror does not have non-trivial connected 2-point function. Then we construct a concrete example of H-mirror with desired properties that is basically a non-quantum error correction and a non-vanishing connected 2-point correlation. And it also produces non-flat entanglement spectrum in some subregions we shown explicitly. Some future perspective is that the imperfect code is an approximate error correction code as well. As this shows up in ADS-CFT, we wish that our model can help to study the subleading effects of ADS-CFT, as pointed out by Janet, all the G Newton effects. And we wish also our model to work as a variational ansatz. Recall that we do have some parameters, the theta and the logical qubits of the stabilizer. We can use them to be the variational parameter to capture some CFT entanglement spectrum. So this is the end of my talk. Many thanks.
Applause. Questions from the audience? Oh dear, it's too clear. Nobody has any questions.
Yeah, probably you ask many nice questions, and I try to explain along the way, and hopefully everything can
And
be clear.
perfect time management. Thank you very much. So
Oh,
okay,
it's just a coincidence. Yeah.
right. One last opportunity. Anyone wants to ask Yixu some questions? Okay, too clear, no questions. So
Oh, thanks a
thank you
lot.
very
I
much.
feel
If we have more questions for Yixu, we can contact him directly. Thanks a lot. So
Thanks a
we'll
lot.
stop here. Have a good night. Okay, wait.
Yeah.
Someone said something. I missed the beginning. Is there a recording? Yes, there is a recording. I will put it up. I'll put a link somewhere. I'll put it on either YouTube or somewhere. I'll put up a link.
Thanks.
Uh,
Thanks. Have a nice day.
okay.
As
Thank you,
well to
guys.
you
Bye
guys.
then. Bye.
Bye.